'Cause you're everywhere to me. When I close my eyes, it's you I see. You're everything I know that makes me believe I'm not alone. 'Cause you're everywhere to me. When I catch my breath, it's you I breathe. You're everything I know that makes me believe I'm not alone. You're in everyone I see. So tell me, do you see me? Turn it inside out so I can see the part of you that's drifting over me. And when I wake, you're never there. And when I sleep, you're everywhere. You're everywhere. Just tell me how I got this far. Tell me why you're here and who you are. 'Cause every time I look, you're never there. And every time I sleep, you're always there. 'Cause you're everywhere to me. And when I close my eyes, it's you I see. You're everything I know that makes me believe I'm not alone. I'm not alone.
So I took this doubling every year and extrapolated it 10 years from 1965 to 1975, from 60 components to 60,000 components on a chip.
First thing you have to tell him is,
Yeah.
guys, we've been giving you a free ride for 30 years while you write your crummy software and we made it faster. Right? That's over.
The future is parallel. Single cores are not getting any faster.
We are going to talk about virtual memory, but before we start, it's always a good idea to remind you where we are coming from. So the last lecture, we talked about some tips of software optimization. For example, you can make your data structure aligned with the access pattern that can better exploit cache locality. So for example, column store, row store, that's which one to choose, right? And in database system, we know we are more into column store because of the pattern that we are accessing is typically select columns. And you can also modify your algorithm to implement a more cache-friendly way, for example, block algorithm. Or you can make your code more predictable so that you can actually use techniques like prefetching to make your performance better. And prefetching is definitely something would help for compulsory misses. And another thing that we can learn is that, well, you can actually change the orientation or the layout of your data structure to make the rest of the code implement execute more efficiently. So for example, before blocking algorithm, we can actually make an matrix transpose to make the further algorithm more cache friendly. So these are all sorts of things that we have learned in the last lecture, and hopefully that will give you some more insights. And last lecture, I think the red team did a lot of good explanation of the answer. So right now everything is every team is kind of close. All right, so today we are going to continue our series of discussion on virtual memory, and let's take a look at this aspect. And this is the code that we have been seeing last lecture, that even though we are giving it a huge array, but what happened is that the code would is killed without any issue. So and some of you already pointed out, well, it's because we have virtual memory. So but if you don't know what is virtual memory, that's okay, because there is no, I don't believe there is a prereq of CSE120 before taking CSE142. So if you don't know virtual memory at all, that's okay. You just need to know there is something in between your software and the processor try to intervene the management of your memory to make this magic happen. And now I'm going to dig into these pieces of code. This is another pieces of a code where we create a process, and then, okay, so this is the pieces of a code that we are going to look into. So we are going to create many processes, and I'm curious about if you know what's the output of this. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to the first vote, definitely that's something we should discuss. So why don't you guys go into group and discuss with your friends? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so I'm inviting one of the group to share your thoughts with us. Somebody home? Somebody there? Okay, so David, what do you think? David? David? Hello?
Sorry, can you hear me?
Yes.
Okay. Yeah. So we said that first, we think that the printed address of A is the same for every running instances. That is true.
Why do you think that's true?
Because I think how should I put this? I guess there's no I guess because I guess each instance refers to like the printf statement, right? I'm assuming. And then so like in between the print statement, there's only like a 10-second or like a 10 clock cycle sleep. So there shouldn't be any I guess page fault. So therefore like at the location, the address of A shouldn't change.
Well, the address location change for a variable in the middle.
Oh. Okay, say that again.
Do you think the location of a variable will change in the middle?
No. Oh, would it?
Okay, so keep going.
And we think that some instances, and then we think that one and 4 is true. So
Okay.
some instances will print the same value of A, meaning that like some instances they'll have different value of it. We weren't really sure, so we kind of just like guessed on this one.
Okay. Kevin, what do you think?
All right, I'm probably going to be like pretty wrong for a lot of aspects of this, but the double is a global variable, right? So A is a global variable, so it's going to be put in the data segment for every process. So every process, when the operating system sets up that process, the A is going to be in the same virtual memory location. And when you print a memory address, if I'm not mistaken, it always prints the virtual memory address, not the real memory address, I believe. And so it's going to have the same address for each of the processes. So the address of A is going to be the same for every instance. As far as the value of A, I don't see it getting, written anywhere. So it's just going to be whatever was previously in memory, in physical memory, where the virtual memory of A for the specific process maps to. So it's whatever was left over there, right? So it's going to be garbage. And if you run it enough, it's going to match up for some of the processes might have the same value of A, but it's pretty rare, I think. But it could happen. So that's my thought.
Okay, so you think the answer probably C?
No. So, O or C, 1 in 5. Different value of A for the most part, yeah. And then address of A is the same. Yeah. So C.
Yeah, okay. So I want to say, Kevin, you are not too far away. And first of all, I think Kevin brought a very good. Okay, so first of all, let me show you this demo. So I have a program here, which is pretty much the same with the program that I demonstrate there. And as you can see here, I have a double A equal to 0. And if you do object dump, dash this program called virtualization. Oh, okay. So let me packet the output to other places, right? You will find, well, a few things that is interesting. If one day you are interested, you can definitely take a look. This is your compiled program. And object dump is a tool that allows you to decompose the binary in a certain way that it will tell you what's the address and where is it there. So as you can see, for each program binary, or say the executable, we have several different sections. Like this is the interpret session, this is the GNU property session, this is the build ID session, this is GNU hash session, this is dynamic symbol session, and in each of the section here, we have several different columns. The first column is the memory address. So remember, when your program is compiled, everything is supposed to be stored in storage, and when you execute it, it's going to be loaded in the memory. And this address is going to tell the system saying that, hey, this is the address that my program wants to run on, right? And this position here, what you will see is the binary values that's mapped to that particular memory address. So for example, for this pieces of a code, at the address of 3E1, you will see 000 in hex. So that's basically what it is. And there are many, as you can tell, there are many different sessions of the code. But in particular, right, you find this. There is a section A, which is the session where we store the variable code A, right? So if you look at this, you will figure out that for every program, every instance of this program, the address of A should pretty much be the same. And A is located in a section called data section, right? So there is a section called data section where we put global memory, variables in it. And there are many other sections, and there are also code section where your, or say the text section where your main function will be located. So those are the composition of your program. And as you can tell, this is the encoding of this program, and you can see, well, for the push, right? So we mentioned that an x86 instruction can be really short, and this is an example, like a push instruction. It's encoded in just one byte of data, like 55. It's the push RBP, right? So it's just 1 byte, right? And for this JLE, it takes 6 bytes, and for this code Q, it has 5 bytes, right? So this is a good enough example to tell you that, well, x86 instruction can be really compact if the instruction itself doesn't have too many arguments. However, if it's an instruction that's really long, then you can definitely see instruction like this is a 7-byte instruction. Okay, so now what we could do is that let's launch the program, saying that I launched the program with 4 instances. And because for the program, when we start running it, it seems like the modern Linux system has some kind of virtual address assignment. So you will see that for the address A, it's not exactly 4030, but you can see it's 030 at the end. So it's definitely adding some offset to the address. And you are low. So typically the Linux system would load would add an offset to your address space nowadays. But if it's the same program, as you can see, if it's the same instance of the same, if it's an instance spawned from the same program, the variable A's address is pretty much the same, because the offset added to the program is exactly the same, right? So you will see every instance of A has the same address. However, if you remember what the program is doing is that we launch a process and we sleep for 10 seconds and we print out the value again. But one thing that you will see is that, well, for this process 68.4, the value is still the same after 10 seconds, regardless of some other processes also try to modify the address of A. Isn't that strange? Isn't that counterintuitive, right? But the answer to this question is that first, the printed address of A is the same for every running instances, and each instance will print a different value of A. And if you are choosing 4, that's not too far away because you are assuming that we don't have a perfect random generator. However, consider the behavior, consider the seed we have done here. It's very, given the instances we have is only 4, it's very unlikely that we are going to have the same value. So Kevin, you are pretty much correct that it's very rare or almost impossible for this case to have the same value of A. And if you will have the same value of A, in our cases, it also means somewhere is broken, right? So for this question in particular, right, what we are supposed to see is that all instances we will have the same memory address. However, we have different values, and the values could be kept, could be preserved after 10 seconds for each different instances. So that's something might be counterintuitive to you, right? So who is making this happen is because we have another layer of abstraction provide an illusion called virtual memory. So what exactly is virtual memory? So first of all, thinking about that, right? Like so what is virtual memory? So first of all, our processor nowadays are running on top of an abstraction called virtual memory. So what happened is that your processor, when you launch a program, we assume the program is executed in an illusion, an abstracted virtual memory address space. So like the 4030 is actually mapped to somewhere in this virtual memory address space. So what happened is that for each different instance of the program, or each different program's instance, we create a virtual address space for each. And if you have learned operating system, each instance of the program execution is called a process, and which means that for each different process, we are going to create a new virtual address space. So what will happen is that your code is executing using virtual memory address instead of its real memory address on a physical memory location. And the processor will work with the operating system to maintain the mapping between virtual address space and a physical memory. So for example, if in the very beginning, if I want to execute a program, then I would load the code into the virtual memory address space, and also the data into the virtual memory address space. But when I say load, this is just virtually load, or say lazily load. In fact, this memory locations, or say this content, won't reflect in your physical memory until somebody starts to use it. So in the very beginning, when a processor executes program A, then the PC will be pointed to the first instruction. And what will happen at this point is that your system, your processor would ask, I want virtual memory address space of A with address 0. Can you give me, I need that. And some abstraction, which called virtual memory, would start to figure out, oh, now our boss needs instruction 0. Where are we going to fetch it? Where are we going to locate it? Where are we going to put it, right? And then this abstraction will figure out where is it right now in the system. And if you are if you are familiar with the volume architecture enough, you know one thing that hasn't been presented here is the storage. So typically, everything is in the storage at this moment. So we load the instruction that we want from the storage and put it into the physical memory. And something similar to what we have done in the cache is that instead of just giving you an instruction, we fetch a set of instruction or a consecutive bytes of data into the physical memory, which we later on call it a page in a physical memory. And then the abstraction would tell the processor, hey, if you want this instruction, here's the place to get it, right? So then I can finally get this instruction and load this page into the virtual memory address space and also have it presented physically in a physical memory, and the processor can start fetching it and executing it. And the same thing would happen when I find that, well, I cross a page boundary and the stuff that I want is still not in a physical memory. Then I would load another page from the storage again. And the same thing would happen if I am executing another program and gradually, and if I have an instruction called load that wants to access data, again, the same process would happen, right? And gradually you will have your data go into your physical memory according to the execution of your program, right? And as you can imagine, because we have limited physical memory space, so similar to what happened in a cache is that we will use LRU, we will use a lot of policies to decide which page can reside in the physical memory. So this is the concept of virtual memory. But the good thing about virtual memory is that we allow your program and your processor to execute in the virtual memory address space. So what will happen is that at a background or in some other concept is that, well, you don't have to tailor your program according to the current situation of your memory allocation. Instead, all you need to do is that I just launch my process or my program, and the virtual memory abstraction would have some kind of translation to translate a compiled memory address or say a virtual memory address to its physical location. So virtual memory, in fact, is an abstraction that for the compiler or the programmer to use virtually, and you don't need to worry about how much physical memory are installed in your system. And your programs, no matter, so nowadays all your programs are executed using virtual memory addresses, and the operating system and the hardware will work together to handle the mapping between the virtual memory address space and the real physical memory addresses. And virtual memory organize memory location into so-called pages. You can consider it similar with the idea of blocks in when we talk about cache. So the reason why we want virtual memory, first of all, it makes multiple applications able to share physical memory. As you can tell, right? Because everyone has exactly the same address in their code, right? So let me show you, right? So for example, in the program that we just dumped, everyone has the address of 38. So this program has the address of 318. And then we dump another program, and you will see that for another program, right, it also starts with 318, 319, 318, right? And if you want to launch the same instance of the same program, you also don't want the execution to intervene with one another, right? So in this way, you need some abstraction to isolate and manipulate and protect the memory location that each program needs. And so if you want to support multitasking, multi-programming, virtual memory is a must. And the second thing, if your program has consume more memory than the installed physical memory, right? Or even though I have sufficient amount of memory for one program, but if I want to run two programs together, it's not going to be enough. You don't want your programmer to worry about that, right? So that's why we need virtual memory abstraction to deal with the dynamic allocation of physical memory location and dynamically move something in between your main memory and your secondary storage. So that's why we really love the idea of virtual memory, and that's why virtual memory is presented in every system. So with virtual memory abstraction, what happened is this. So saying that today you have a processor running a program, say I load the address of 9. And this 9 is actually virtual address. And your processor would know where in a system we have something called page table. And the page table would provide some kind of abstraction that would tell you where in the physical memory can you find the page containing the address of 9, and then pointing your memory access to that particular page, and finally return the data that you want. So that's the concept of virtual memory abstraction. And modern mechanism of handling virtual memory is exactly like several slides ago, the animation that I showed is called demand paging. So the basic idea of demand paging is very similar to the idea of caching. It treats the physical memory as a cache of virtual memory. And the virtual memory, you can consider the complete set of your program is now on your secondary storage. For example, your flash SSD or your hard disk drive. And we have learned the term of block in cache. And in virtual memory, we partition the address spaces into pages. So you can consider the block is like a page in your virtual memory abstraction. And the page table, which we use to look up the location of physical memory to virtual memory, then that's considered something like a tag array. However, what's different from virtual memory and a cache is that for virtual memory, a memory page can go anywhere in a physical memory location. So it's a fully associative cache compared against the set associative cache that we have seen in when we talk about cache. So that's the idea of demand paging. So with that, what happened when we receive a virtual address in when we execute a program is that we need some mechanism to translate the address into the physical location. And as I mentioned earlier, there is something called page table to help us to achieve that lookup. So what happened is that processor received a virtual address from the running code, and main memory would use the physical memory addresses to look up the data. So, and because virtual address space is organized into pages, right? So every bit so we also have something called page offset, right? So you can ignore, so whenever you receive an address like this, right? You can consider that, well, several bits will be used as a page offset, and because they are within the same page boundary, everyone within the same page will share the same page number. So we partition the address into two fields, virtual page number and page offset. There's no index here. And because remember, this is a fully associativity cache. We only have a one set, right? So the page offset won't be translated. However, the page table will contain the translation between a virtual page number and the physical address. So after this lookup, I will be able to find out where in the physical memory I can find the virtual address. And this page table is maintained by your operating system, and the operating system and the processor has a consensus where the page table is located and what's the content of the page table, so that the processor can automatically go to that address to perform this translation without always having to ask the operating system for that. So now let me ask you a question. So given a page table like the previous slide, can you imagine how big the size of a page table must be in a 64-bit virtual address space? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's have a group discussion and let's see what do you guys think. Well, let me send out the screenshot real quick. Okay, so let's have a group discussion, and before going to the group discussion, open the file that I sent out through the chat. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, well, I still see a very diverse answer from you guys. So we definitely need some group to share your thoughts with us. All right, so I have Kevin.
All right, so how I approach this is there's 64 bits in the address space, and a page is 4 kilobytes. So that's 2 to the 12, and so the last 12 bits of the 64-bit address is going to be like the offset within the page, right? So that leaves 52 bits. So those first 52 bits are going to be a unique page number. So if the page table needs to hold a unique translation for each individual page number to a real address, real physical address, then there has to be like 2 to the 52 entries. And then on top of that, an entry is 8 bytes, which is 2 to the 3. So it's like 2 to the 55 is like how large this page table needs to be.
Right.
Which
So
is huge. And then also
I have
one more question too. So another thing is every process is going to have access to this 64-bit address space. So shouldn't the page table like translation also incorporate like the process ID or some other unique identifier if all the processes are sharing the same virtual address space?
So let me give you a clear, okay. So I guess one thing, there is something to do with your operating system teacher. And I found, because I also taught operating system in my home department as well. So one thing I found that's really not polished when we teach undergrad operating system is that one of the purpose of virtual memory is protect one process from another. So every process would have its own individual page table. Each process would have its own individual page table. So to the answer of Kevin, there is nothing regarding sharing a page table because each process would have a unique page table. So in fact, if each page table for a process is this large, then depending on how many processes you have, you will have that number of process times this amount of memory. But in fact, first of all, for each page is 4 kilobytes. So, and 4 kilobytes is 2 to the 2 times 2 to the 10 bytes. So you would have 2 to the 12. And when we say virtual memory address space with 64-bit, it means that you can have 2 to the 64 bytes of data and instruction in your virtual memory address space. So you would have 2 to the 64 divided by 2 to the 12, this amount of pages to address. And then each of the page table entry is 8 bytes. So it would take 32 petabytes. And remember, each process would have its own page table. So first of all, a single page table is already big enough. None of us has petabyte level of memory. I think most of us are still stay at the gigabyte level. But if you do have terabytes memory in your main memory level, I do want to know your parents because I think I found something interesting. I found someone would be helpful if I want to make a startup company. But the thing is that, you know, the page table is really large and it's too large to a degree that it's almost impossible to accommodate that in our modern memory hierarchy, right? So now, this is too large, right? And and there are a lot of difficulties to make such a big table. So first of all, right, if you look at the process of lookup, we want everything to be consecutive, and it needs a big segment. It's very difficult to find a spot in your memory, and it's also too big to fit in your memory if your address space is large, right? So it's not going to work, right? So we have to be creative in how to make the page table happen, right? So sometimes we do have to think about, well, so in the last lecture, I keep criticizing how bad the tree structure is, how bad the linked list is, right? But they are there for a reason, right? We taught you this in data structure class for a reason, because they are indeed cases where we need them. So to accommodate page table, that's where we do need them. So let's say, right, like if I have a 64-bit address space, I need this amount of leaf nodes, right? However, it's almost impossible to consecutively store them, and they are too big, right? So there are two things that we have done, or say two advantages that we take from the real program behavior to make the page table idea still feasible in modern systems. So the first thing is that we found modern programs, although we do have 2 to the 64 address space, but how many of you ever wrote a program that would use out all the 2 to the 64 byte? The answer is no, right? In fact, this is how we lay out our data most of the time. And as you already tell something from the object dump result, in the very beginning, we have code section. And then at the end of the program, we have the static data section. So for example, like the global variable A that I declared in the process, in a sample process code, it's in a static data section. And then followed by the static data section is actually a heap section. So if you have functions like malloc, your address would come from the heap section. And at the end of your virtual memory space, there is a stack section. So whenever you make a function call, or whenever you have a local variable, it's coming from the stack section. And for the memory allocation from the heap, it keeps going from the lower end of your address to the higher end of the address. And for the stack section, it always goes down from the very end of your virtual memory address space toward the lower end of your virtual memory space. So what does that mean is that typically this is how your program use the memory address. I gradually use consume address in the very beginning. I gradually consume address at the very end. However, the large portion of the middle section is never used. So so what would happen is that so this is the advantage we can take. Oh, I hate this animation. So what will happen is that, first of all, there are several tricks that we make, right? One, it's hard to find consecutive address to store a big chunk of page table. So we make the page table entries also page-based. So we break up entries into pages, and each of the page will contain a few page table entries. So for example, a page is typically like 4 kilobytes and is the basic unit of memory access and of memory access. And if each of the page table entries is like 8 bytes, right? A 4 kilobyte page can store 512 page table entries. And the second thing is that this is just the leaf node that we have. How do we know where it is, right? So well, okay, let me go through this way. So first of all, right, what happened is that, okay, it's also So first of all, instead of pre-allocating consecutive address space for big chunk of page tables, right? What happened is that when I access the code, I start to allocate this page table entries, or say those leaf nodes on demand. And each leaf node, as you can see here, is a collection of 512 page table entries. And whenever you have additional requests, you gradually allocate this page table node entries. And if you never use this middle section, you will never have to allocate the pages of page table entries, right? So in this way, this level of leaf nodes would reflect exactly the same amount of memory that you consume in a virtual memory's address space. However, another difficulty here is that these leaf nodes, they are spread out and we need to locate them in a memory, right? So if you look at this data structure, you already have some feeling of this. This is like a B tree, right? So in fact, we organize page tables nowadays into B trees. So what will happen is that, so for example, if we have 64-bit address space, we have 52 bits of the page table, we need 6 label of B tree to accommodate the whole page table. So what will happen is that you will divide your page table, virtual page table number, virtual page numbers into different levels of index in a B tree until we reach the end of the leaf node. So here's an example. So in x86-64, nowadays, although we say it's 64-bit, but they also cheat in a certain way that modern x86-64, they only use 48-bit, effectively only use 48-bit. And the reason is because their observation find that there is almost no program use more than 2 to the 48 bytes of data and instruction. So what happened is that in your processor, there's a specific register that tells the executing program, where can I find the root node of my page table, or say the root node of the B tree, and use the 9 bits, which we partition through the address as the index to in the root node of the B tree. We can find the next level location of the B tree node. And again, we use another 9-bit as the index to this table to find the next level. And gradually until we reach the last level of the B tree, where we have the translation of the physical page number. And that's how we perform the lookup. And with the B tree structure, the good thing is that we don't need big tables, and we only need to allocate as many leaf nodes as we need in the virtual address space. So now another follow-up question that I want to ask you. For an x86 processor that we just demonstrated, how many memory accesses do you think we will trigger during the execution of an x86 move instruction? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to the discussion result, we definitely looks like we need some kind of group discussion. So go do it. All right, let's wrap up in 15 seconds. Five, 4, 3, 2, 1. Time is up. Okay, so now I really want to invite a group to share your thoughts with us. Any group would like to share your thoughts with us? Well, if not, then I will definitely use our random. All right. All right. Team Red. Anyone in Team Red would like to share?
Sure, I guess.
Okay, Debbie, you are the representative. What do you guys think?
Uh, we think it's mm, hmm. Probably 4 B.
B. Okay, so why is 4?
We're so we're thinking that hmm, is that so if you have a wait actually we didn't think about I guess entirely. So I guess the thought process is that if you so if it's a move instruction, then so first we have to access like I guess the page table in order to see
Mhm,
the virtual to physical translation. And
mhm.
then afterwards we need to I guess either access the physical memory when if it's if it's inside the physical memory, or we have to access the disk
Mhm,
if in the physical memory. So
mhm.
so I guess in that case it's two, or it's a bit weird.
So you said we need to access the page table.
Yeah.
And we may need to access the stuff, so it's two.
Mhm. Cool.
Okay. So when you access the page table, how do you access the page table?
Um, we're not sure. I'm not sure.
Do you
Ah,
remember this guy?
yeah. Ah, I see.
So how many memory accesses are here?
This is 4.
This is 4, right? And if your data is in the memory, how many?
It's 5.
5, right? So that's for data access. But how about the instruction itself?
Oh, so you have another one.
Right. So the answer is that we have a total of 10. Right.
Oh,
So
I see.
right. Right. So here's the thing, right? Okay, thanks, David. So here's the thing with virtual memory abstraction. We don't have to worry about how big of the memory we need to use. However, no pain, no gain. There's no free lunch, right? The cost here is that supporting this abstraction, we need more memory accesses. You may need to have 10 memory accesses for a single instruction. So remember how slow it is? It's 100 cycles or 50 cycles, doesn't matter, right? So, well, let's say 50 cycles, right? Then if you have 10 memory accesses, it means that executing an instruction itself would take about 500 cycles. Your CPI is always 500 at least, right? And okay, and now we have cache, but remember what cache does. It caches the instruction, it caches the data. It doesn't cache this, right? So you still have 400 cycles that you will suffer in this way. So that's definitely not going to work in our system, right? So the most important thing is that we have to avoid the address translation overhead in our memory hierarchy design. So what happened is similar to the idea of cache, that we create a small cache called translation look-aside buffer. It's a small SRAM cache that stores the most frequently used page table entries. So you can consider we have some kind of cheat sheet here. Whenever the processor core need to ask for address to access something, again, because we use virtual memory address all the time, right? So the TLB will translate that to the real address, and then we can use that to access L1. And so the good thing is that it's a lot faster than having everything going to the DRAM stored page table. However, the best thing is that we have someone in the middle, right? So it's not fast enough, right? So another idea that we have is called virtual cache. So we allow the L1 cache to accept virtual address. And in the meantime, the TLB will perform address translation. Only if the L1 misses, we would use physical address to locate data in the L2. However, it seems reasonable, but the sad thing is that, as we tell, right, as I show you, there are many programs, they both have the same address like 0x318. There are many programs that are even created from the same static program. So they would definitely have the same virtual addresses all the time, but they should be pointing to different physical memory addresses, but you only have one set of TLB. So it's get confused, right? And of course you can you can always set up and so when in your L1 cache, there may be cases that, well, if I use virtual memory address, I don't know the data right now here belongs to which running program, right? So then that's really problematic. So the real solution we have here, right? The real solution we have here nowadays is something called virtually indexed physically tagged cache. So the basic idea of virtually indexed physically tagged cache looks like this. So let's go back to the very beginning of the definition of a very basic page table. And remember, even with hierarchical page table, it's an optimized version of this basic page table. So remember, this is the process of address translation. We fit the virtual page number into the table to look up the real translation, but the page offset remains the same. The page offset remains the same, right? So there is part of your virtual address will also be part of your physical address. So the page offset in your virtual memory address will never change before and after translation. So something we want in our memory hierarchy design is that we want to use the unchanging part to look up the cache so that we can have the address translation and memory access or cache access performed concurrently. So what happened here is we design our cache in a certain way that we make sure the set index and the block offset both sits within the range of page offset. On the other hand, the virtual page number is now considered like a tag, right? Or say, well, sorry, the page, not the virtual page number, sorry. The page number is considered like a tag, right? So what will happen is that whenever I fetch a block, I use the physical address to fit in the tag field of my cache. And when I access the cache, I use the set index and block offset so that when the address translation is done, I can compare my tag based on physical address with the TLB search result. So to this end, my cache is still using physical address, which avoid the case where many processes would have the same virtual address, but also avoid the case where we always need address translation before access the cache. So this is what would happen. With virtually indexed physically tagged cache, when I get an address, still partition it into offset index and tag. Or you can say the tag right now is a virtual page number. And with the set index block offset, I can still access my cache. And in the meantime, I use the virtual page number to access the TLB. And the TLB will store the physical page number of the virtual page number. And in fact, the page number is the tag field of my cache. So it turns out I can compare and see if it's a hit, but still make the translation concurrent. So that's the good thing about virtually indexed physically tagged cache, is that it allows the L1 cache to still use physical address to index and compare the tag. Avoid the aliasing of virtual memory addresses from different programs. However, it also avoid the translation happen in a critical path. So that's the good thing about virtually indexed physically tagged cache. However, again, no pain, no gain, right? With virtually indexed physically tagged cache, because we have the enforcement that your set index and block offset must be within your page offset. If you use C equal to ABS, it means that log S and log B must be within 12 bits. And if you have a direct map cache, which means that the A equal to 1, then your cache size can only be 4 kilobytes. So that's the restriction of using virtually indexed and physically tagged cache. So now I want you to look into this. If I want to build a cache with 32 kilobyte capacity, and I also want it to be virtually indexed, physically tagged, what are the available configuration to build this cache? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looking at your answers, I do believe we need some kind of group discussion. So go ahead and do it. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so now I need a group to share your thoughts with us. All right, if not, okay, Kevin, you saved this.
Okay, yeah, I can go for it. So the page size needs to be like the limiter on this system is the fact that the page size needs to be the same size as your index and offset, right?
Mm-hmm.
Which is 2 to the 12, or it's going to be 12 bits, because 4K is, 2 to the 12, and your entire capacity is 2 to the 15, right? So you're pretty much limited in the fact that your associativity needs to be 2 to the 3, which is 8-way associativity. But you can wiggle the other numbers around, I think. So instead of like 64 bit blocks, I think you can do 32 byte blocks, but you'll have twice as many sets, but each set is still 8-way, right? So you could wiggle the other numbers in terms of like how many bytes are for the index, which is the number of total sets, and how many bytes are for the offset, which is the block size. But I think you're limited on the 2 to the 3 for 8-way associativity.
Right. So the key thing here is that we want the log B plus log S equal to 12, right? If you remember the corollary that I put on top of the C equal to ABS, because our block index, block offset and set index must be within 12, right? So given that's the restriction of physically tagged virtually indexed cache. And if you examine each option, right, for A, the block offset is 5. The block offset is 5. The block offset here is 6. The block offset here is 6. And given you have 32 kilobyte, so this gives you, if you have 2 ways, right, then this would give you, and 32 is like 2 to the 15, right? So this would give you 9 bits in the index. This would give you 8 bits in the index. So both of this is 14 or 13, right? So it will not be working out for the virtually indexed physically tagged cache. And for this one, again, right, if you use C equal to ABS, you will figure out it's 7 in the index, and it's also 13 total, right? And for this one, that's the only one that would give you 6 and 6, which fulfill the requirement of 12 in block offset and set index. And another way to look at this, right, is that, and this is exactly how Core i7 processors configure its own cache, right? So, and in fact, modern processors like AMD's Ryzen processor also has this size of this configuration of their L1 data cache to in favor the design of virtually indexed physically tagged cache. So if you see this, you will figure out that a lot of our memory hierarchy design is not determined by a single factor. In fact, they are determined by many, many factors in the system. And this is an example that how the cache size is limited because of the virtual memory system design. And if you use equal to ABS, it's easier to tell that you need A equal to 8 if you want the cache to format like to support the virtually indexed physically tagged cache. All right, so that concludes everything that we want to talk about before the midterm. And a lot of you are here because you care about the midterm. And here's the format of the midterm. It will have 10 multiple choice questions. And okay, Kevin, question?
Oh, really quick question, piggybacking off the last slide. So is 4 kilobyte page size pretty standard across all systems then? If
Yes.
processors are designed around that? I'm guessing like all
Yes.
systems have that size page. Okay.
That is true. So far, yes. But the answer may be changing in maybe next decade because we have growing our memory capacity a lot and people are talking about huge page. So in fact, modern processors like x86 processors started to support 2 megabytes of page sizes. So that may be changing in the future. But right now, most of the operating system would use 4K. All right. So about the midterm, we will have 10 multiple choice questions and 4 short answer question and 3 homework style free answer questions. And I don't think we need to mention too much about how to be a good answer for homework style free answer questions, because first of all, we cannot guess what you think. So if you figure out that, well, I want regrading because you can see, I know this, I just didn't write it down. Okay, that's not a good reason, right? So you say, well, we have limited page size, we have limited page, but this time it's all on grayscale. So you can put as many words as you want. And so try to be as complete as possible when you are answering these free answer questions. And show your work. So you should be able to get some partial credits, even though your final answer is not correct. But if your intermediate steps looks reasonable. But if you don't have intermediate steps, you will not get any credits, even though your final answer is correct. All right. So here's a sample midterm. So first of all, you will get like 10 of those multiple choice questions. And then another big section is short answer questions. So for short answer questions, we require you to limit your answer to 30 words. And I also put this on the exam that if you have more than 30 words, you will receive 0 in these questions. And I just want to let you know, I will pick 4 out of these questions that I listed on the slide. So please brainstorm from now how to address, how to answer these questions properly within 30 words. And MDOS law, we spend a lot of time in both the lecture and the lab, how to do it. We talk about the definition of speed up, how to calculate it. Well, you burn a lot of the brain cells on this type of questions. Practice it again. And again, it's really important for us to know how to optimize your code. And first of all, you have to know how good or how bad your code is using modern caches. So that will be the sample midterm. Other than that, before you leave the classroom, assignment 3 is a very good tool to force you get familiar with the interface of midterm, which you will be using LaTeX equation and markdown syntax that are currently supported by Grayscope. And those are very good tools that you should be using in the future. Like a lot of GitHub documents are using markdown syntax. And also our midterm will start Wednesday, 5 p.m. till Thursday, 3:20 p. However, you have a time limitation. Once you start, you cannot stop until 80 minutes later. And you cannot restart in the middle. You only have one shot, and you may review. And the thing is that everything, everywhere we mention in the class are really important. And okay, so some of you, well, I think I mentioned 4 of the midterm question, or 4 of the short answer question will be 4 question would be the short answer. Well, 4 question out of the slide would be the short answer questions, right? So some of you asked about that. And okay, so other than that, if you don't have any other question, I will talk about a midterm review tomorrow, which give you a 80-minute quick review of what happened in the past 2 weeks. All right. If not, I will see you tomorrow.
Hey, Professor, can I ask a quick question?
Okay.
It's about the last content, the last question. It said the operating system used 4K pages.
Mm-hmm.
Does that automatically means the page size is 4 kilobyte? Because I feel like
Yes.
it's oh yeah, it's okay. Yeah, that's all
Yep.
my question. Thank you.
Okay. All right. See you guys tomorrow.